Hello everyone. This video we are going to continue to talk about the ballistic pendulum. Okay. And the ballistic pendulum. In the previous video we answered the A/B question. Okay, not A question, A and B problems. And here is the C problem. Yeah, like I said in the previous video, okay, the ballistic pendulum, by measuring the edge, you can back calculate the incoming velocity of the bullet. So apparently there's a relationship between the h, the swing height h, and the incoming velocity v. So what's the relationship? Okay, find a relationship. Okay, and the C problem. Okay, so how to solve the C? Okay, let's start it. Let's start it. Let's start it. Okay. Okay, so how to solve this problem? Okay, so the C is trying to find a relationship between V and H. Okay, and we use the energy. Okay, for this problem, you find from V and H. So, like I say in previous, I say okay when the bullet strike into the capital M, and then this whole system will carry a velocity, and then the whole system is go to the swing up to the height h. So this is an energy transition problems. Okay, so when the bullet strike into capital M and carry a certain velocity, so you have kinetic energy, and this kinetic energy, and then the whole system swing up for height h. So that means the kinetic energy will transform to the potential energy. So actually, actually you want to find a relationship between V and H. Actually, this is an energy conservation problem. Okay, so let's start. So let's start using energy. We will start using the energy conservation. And we now consider after collision. Okay, after collision. Wait, after collision. Okay, we'll consider the situation after collision. That means uh, so after the M strikes into capital M. Okay, we consider this part after the bullet strike into capital M and the whole system start to moving up with height h. Okay, so and the whole system. Okay, so there is no friction and there is no external force. The work done by external force, so it's a mechanical energy conservation. So we'll use the mechanical energy conservation. Mechanical energy conservation. Energy conservation. Okay, what's the equation for mechanical energy conservation? Don't forget, it's delta K plus delta U is equal to 0. Okay, that's for mechanical energy conservation. Okay, the delta K and delta U, so you need to calculate, like I said, in this mechanical energy conservation problem or energy conservation problem, you need to consider, you must list the kinetic energy and potential energy for your initial state and final state. Okay, so let's list this. Okay, let's list this. What's the okay? So initial state, final state, initial state, final state. Okay, and here we need to address this. What is the initial state? Like I said, we consider we consider after collision. After collision, that means after the bullet strike into the capital M. We start. That's when the bullet strike into the capital M. That's our initial state. Okay, that's our initial state. After the maybe I should. When at the moment at the moment when M strikes into capital M. Okay, that's our initial state, and our final state is M plus M swinging swings to height h. Okay, that's our final state. Okay, so initial state is just right at the moment when the small n strike into the capital M, and then it causes a swing up to height h. That's our final state. Okay, so at the initial state, do we have what's our kinetic energy? What is our kinetic energy? Okay, so when and in the last video we say when the bullet strike into the capital M, at that moment, this whole system carry a velocity, so it must carry, so it also has the kinetic energy. So in your state, what's our kinetic energy? 1 over 2, because the M is struck into the capital M, so it's M plus N. And what's the velocity? In the last video, we already calculated velocity. I hope you remember the answer. Okay, in last video, we already calculated the velocity, mv square. Okay. And what's our potential energy? Because in this system, we don't have a spring, but in this problem, we have to consider gravitational potential energy. And what's our gravitational potential energy? It's related to our coordinates. So let's say this is y. Y doesn't change the color. Okay, okay. I suppose this is y direction. Okay, moving h, and here is our zero. Okay, origin zero. Okay, so when at the moment when we just consider when the moment the M strike into a capital M, and then it's the moment it doesn't change that, it doesn't have change the position that much, so it stay in this horizontal line, so the potential energy is zero. Okay, because we set origin here is zero, mg0. Okay, I should say mg0 and g times 0. Okay, that's our initial state, potential energy and kinetic energy. Okay, I just write 0. Okay, at the final state, what's our kinetic energy at the final state? Okay, like I said, when the bullet strike into the capital M, the whole system slowly swing up to the position, swing up to the height h, and at this moment, at the height h, it will stop there. Yeah, it will stop there, and you will have a very, 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 very instant moment at the height edge, the whole system stopped just right here. And at that moment, it will lose its velocity. It will not have no velocity. So at this moment, no velocity means no kinetic energy. But at this moment, we have the gravitational potential energy is m plus m, and its g, and its height is small h. Okay, so hope you can recognize this. After the collision, after the inelastic collision, it will become energy conservation problem. Okay, you carry a velocity or kinetic energy and transform to a potential energy. Okay, and so okay, we can put all the information into the delta k plus delta u equals zeros. Okay, so k final state minus initial state. So final state kinetic energy 0 minus, yeah, I should write more detail. Okay, kf minus ki plus uf minus ui equal to 0. Okay, so what we have, move up. So we'll have 0 minus 1 over 2. So this will be m plus m mv square, right? Okay, and plus the final potential energy is m plus m g h, n minus 0. Okay, and is equal to 0. Okay, so as you see, using the energy conservation, we will certainly reach the relationship between the h and v. Okay, we will see it. How to express this relationship? Let me see. Which one is better? Okay, which one is better? Okay, I see. Okay, so, we will have get this m plus m square v square equal to m plus m times g. hg is a gravitational acceleration. Okay, so so we will find v square is equal to m plus m square and m square and gh. That's more beautiful format. Okay, m plus m square gh. Okay, so you will finally your v. Maybe I use another color. I use another color. Okay, v equal to okay m small m plus n and square root of gh. Okay, so that's why I say in experiment by measuring h, you will get the velocity. This is the measure. EASURE. By measure h, you will get velocity because capital M and small m and g are all given. It's all known information. Okay, by measuring h, you'll get the velocity. Let me check the formula is right or wrong. I'm just very afraid I calculate something wrong. I did calculate something wrong. Yeah. I just missed something. Okay, what did I miss? Yeah, I missed this. Okay, okay, so okay here too. Yeah. What did I miss? All right. What's it? So we put the square root of 2 into here. Okay, so that's very important because you didn't have this factor, you are also wrong. Okay, so let's measure the ASURE. Okay, check. Is it right? Yeah, that's right. Okay, so that's a relationship between the height h and incoming velocity of the bullets. So this is problem C. Okay, so this is using energy conservation to find a relationship between the h and v. Okay, so and for the ballistic pendulum, we will have another video. Okay, in the next video, I will use this ballistic pendulum to introduce a concept called internal kinetic energy. Okay. In next video, internal kinetic energy, we will introduce a new term called center of mass frame. Okay, it's center of mass frame. It's not center of mass. It's a little difference. Okay, center of mass frame is not equal to center of mass. Okay, we will introduce the internal kinetic energy in next video. Okay, so see you in the next video. Bye bye.